Buenos días con cada uno de ustedes. Vamos a esperar unos minutos hasta que ingresen los otros. Buen día, profesor Alejandro. Alexander.
Hola, buen día. Hola, Roberta, buen día.
Olá, bom dia. Bom dia para vocês. Tudo bem?
Bienvenida.
Obrigada. Eu perguntei no chat qual é a melhor forma de que vocês usam para fazer a apresentação aqui. Porque eu não estou conseguindo compartilhar só o PowerPoint.
Mi portugués no es muy bueno. Maybe we can speak in English sometimes.
Maybe I'm here in Spain and I just speak in English because is hard.
Okay.
So I'm trying to share my presentation,
Okay.
and I don't how I can share just the PowerPoint app.
Yes.
I can share my whole screen. It's like that.
Okay, maybe we can try and see how it behave. Now we are not online. In a few minutes, we
Okay.
will broadcast online, and now it's time for making some tests.
Yes, so let me try because I have a lot of things in my desktop. So because I think that if I share like a presentation, I don't see you or no, just because I said it's broken, now works. Let me try this, like this, okay? Or like that.
Buenos días. Bom dia.
Buenos dias, bom
Roberta.
dia, bom dia. Aqui é boa tarde, mas bom dia para vocês.
Não. Você
Não,
está em...
em
Você...
Bilbao,
yeah, okay.
just in these 2 weeks. It's work the presentation?
Yes, it's working.
It's working, so nice. So,
Ok, Alexander Hernández es moderador. Ok, muito obrigado
okay.
por aceitação da palestra. Obrigado. Voy a estar
De
background.
nada.
Ok.
I think that I can look the presentation. I also seeing you on the screen.
You can see
I
the
don't know if-
presentation?
Yeah, I can see the presentation. And also I am seeing you I mean, in front of the presentation. James, if you agree that it's okay this way.
Let me stop sharing and let me try another thing here.
But that
No,
way,
I have maybe this will work like that.
yeah. Okay. Now we are seeing the presentation, and I mean the screen of Zoom with the face of you.
Okay.
I think that this way is better because before I was seeing you twice.
See. No. I think that it's okay. Maybe if the people can hide this part of the video to see just the presentation.
Yeah.
I try here and it's
I
okay.
think that depends of the configuration of each person. For example,
okay.
in my case, I am only seeing the
Presentation.
The presentation and a small square with you below.
Okay.
But I think that depends of the configuration of every person.
Okay. So now everything is working. Let me see.
I don't know where you already saw Luis. I don't know if the other panelists want to present to Roberta.
I think that you, Alexander, because you are a moderator today.
Mm-hmm.
Okay, and I am contacting Melvin, who is the technician for the streaming. But let's wait for him for a moment, okay?
Okay. But now we have Stuart Holmes that is present today already.
Dias a todos. Good morning, good afternoon, wherever you are. Roberta, I look forward to hearing your talk. Thank you. Thank you, Alexander.
Welcome.
Yeah. Augusto is also there.
E aí, tio?
And Gabriela Grad, and she's from Argentina, Córdoba, is also present.
Hello, how are you?
Hi, Gabriela.
Hi.
Ok, ya creo que ya puede empezar porque se está grabando y luego van a subir la grabación.
¿Sí lograste algo?
Alexander, ya puedes la orden.
Bueno, bienvenidos a la charla de hoy de la Red Latinoamericana de Física de la Materia Condensada y Ciencia de Materiales. La red LAFMAT es una comunidad que tiene como objetivo divulgar los avances de vanguardia de los investigadores latinoamericanos y facilitar la interacción entre investigadores latinoamericanos y destacados investigadores de todo el mundo. La red está integrada por investigadores de la Universidad Mayor de San Marcos, en Perú, la Universidad Federal de Pernambuco, en Brasil, la Universidad Rural de Río de Janeiro, también en Brasil, la Universidad Fluminense de Río de Janeiro, la Universidad Nacional de Colombia, el CIMBESTAF de México, la Universidad de San Sebastián en Puerto Montt, en Chile, la Universidad del Zuila, en Venezuela, el Centro Atómico de Bariloche, en Argentina. Y en el día de hoy es una alegría presentarles a la doctora Roberta Pereira Díaz. Roberta es profesora de química en la Universidad Federal de Pernambuco y tiene un doctorado en ciencias químicas. Su investigación se especializa en química computacional con un enfoque en el modelado molecular de materiales. Tiene experiencia en la simulación de materiales biológicos y blandos utilizando dinámica molecular y métodos híbridos, QMMM, Quantum Mechanics, Molecular Mechanics, para investigar sistemas y procesos complejos. Además es codirectora del grupo de investigación HIM, donde trabaja en el desarrollo de enfoques innovadores para el modelado molecular y la investigación de materiales. Y el título de la charla de hoy es Explorando nuevas perspectivas para entender la membrana de LPS. Así que bueno, bienvenida Roberta. Es una alegría tenerte con nosotros hoy.
Thank you very much for enjoying me, invite me. In the presentation, what is better? I'm trying English or in slow Portuguese?
As you prefer.
Okay.
It's up to you.
I forget this detail to play my my presentation. So sometimes I think everybody will understand better my English, not as fluent English, but maybe it's better for everybody. So I try. If everybody, if anyone has a question, can talk to me. And, I will try answer. And now I have my colleague Augusto, then speaking Spanish fluently now, and can help us to translate.
Thank you.
So,
Thank you very much.
yeah, it's okay. So today I will try and speak a little bit for you my work about the how molecular mechanics can help us understand the atomic environment of different kind of materials, in specific LPS membrane, and why you chose this membrane, LPS membrane. This is this membrane of LPS. LPS membrane is from the Pseudomonas aeruginosa bacteria. So we can see in these graphs we have a lot of the resistance, and a lot of I forgot in English how I speak in this. Vários antibióticos, antibiotics, the membranes of diferentes bactérias começam a ter diferentes resistências para qualquer modificação que a gente tenta fazer com elas. So, what I try to speak is when you try change the chemical surface of your medicine, your antibiotic, you can provoke a change of the surface of these bacteria. So, and with the time, the bacteria grow up with different modifications and it turns a lot of more resistance. And you have a problem in the world because you need always more strongest antibiotics, and there is a fight don't have an end because the surface of the bacteria always try change to fight with this new medicine. So you never what it is problem in the world because you have a disease that don't have a solution to treat. So you need to understand how is the mechanism to understand how we can stop this or slow this fight. So this Pseudomonas is a bacteria too dangerous and have a very ugly disease. And if I don't put in my presentation because it's too ugly, but if you see in the Google, if you put the Google, you can see how this affects the surface of your membrane or your skin. And if you don't treat quickly, you can go to the death. So, and these membranes, the outer membranes is made of lipopolysaccharides molecules and have this a lot of range, a large range of these surfaces just for one kind of the bacteria. So bacteria is something very, very small, but is example, this green one is an example, just one unity like that. But so the computational chemists or scientists, this bacteria is too big to study. So what you see, how you can approach this is with it's a little zoom. Let's see if I can screen pointer. Just I mean, I forgot this. Like this. So you can use now just we understand how the surface, the green surface works with the environment. Maybe you can propose some mechanisms different to adhesion of these materials, these soft materials. So if you start this, you can see this one like an atomistic way. So this for me, a bacteria look like this, and this is enough to our model to understand the different properties of this material. So just for you guys understand how is different the view of this kind of scientist is all this structure is like the green one here if you put some scheme. So what I propose to study is just like this. It's just like this, but is almost 3,000 more than, of course, more than just for one model. So 3 times 300,000 of atoms. So it's too big for us. If you change this sugar of the surface, you can change the chemotype of your bacteria. So this is one structure of our bacteria. For example, this is lipopolysaccharide. The part of the apolar part is like a lipo, é a parte da gordura, né, do lipídio, is a lipídio like this, and this head is where you put the sugars, the units of the sugars. So you have to kind of study here. First of all, you study with quantum chemistry to understand this one part of molecule, and because our tools of molecular mechanics don't have these molecules already, so you need to study this specific way to put in your potential, in your first field, essas características específicas da molécula. Então, a gente começa assim. I don't know if you have some familiarity of this kind of study. When you grow up, the size of your system, you need to change your model. So if you have small molecules, you can treat this like quantum chemistry. But if you have more than 100, maybe you need to put some more the modeling, use model more that don't use more electrons, you put some potentials to understanding. So in my case, I study with all structure with all atoms. But if you have more and bigger problems, you can use another model, is molecular model too, but a coarse grain. Coarse grain, you mean that in some case, depends of your model, you can change a CH3 group for one sphere that represents these potentials and the volume of these groups. So you can have some gain to study your work. So you have this is a kind of problems of if you have a big structure. If you have a small structure, it's more easy to walk about the surface of the potential. So it's more easy to understand or find the minimum potential. But in large systems, you can find it's more difficult because if you have a lot of atoms, you have a lot of dimensions, so it's more difficult to find where is the minimum. And don't have any sense for us in materials study one minimum because all the process is dynamics. So you have with dynamics you can map the surface to understand how is more possible structures you have. So now this already talk, and you have a molecular simulation, molecular mechanics. You can choose just optimize it one molecule, but now to understand how the big problems works with the time, you use these equations to modeling your molecule or your system beyond these potentials. So you use a force field, a specific force field to describe your kind of models and describe this along of the time. So you can choose how your molecule or different parts of your model you will work with the stretch, the angle, the torsion, and you don't have electrons here, but you use a non-bonded force that is so important to problems of the surfaces. So you can, this is a kind of the surface of potential. If you use a lot of atoms, you have more complicated, more specific surface, but you use a coarse grain, you have a more modeled, more soft surface. Maybe you can find your answer with model more general more general model. So everything depends of what is your problem and what your question basically is this. So this is a example that I show you how the membrane works. This is a membrane, a more simple membrane that might work, this, and how this works, because for us, those to answer how the antibiotic is active in the surface of our bacteria, for us don't have any sense that one structure for unique structure of the whole problem, because you want to see how the behavior of what your membranes. So one picture like optimization don't have any sense, and you can find this optimization because the process is dynamics, you know. I really hope that I make me clear here. So now, and to see, you use these equations to see how the behavior of the atoms beyond your force, intermolecular force, act in your surface of membrane and use antibiotics. So see, the movie started. So these peptides started in the surface, and of course the water here is around all the structure, embaixo, em cima, but I hide it for we can see how this work. So the intermolecular force is so strong in this case that the peptides prefer start the combination with the surface of membrane, then have interaction with another peptide. So what is happening? How can you see in the movie? The interaction is so strong, then another parts of surface of my membrane prefer contact with my peptides. So elas se dobram, assim, they fold. And this can, of course, we can see the breaking of the surface of membrane, this because you have just a small piece of this membrane. But this is kind of the membrane ruptures, broken the surface. Então, sofre essa ruptura. E uma vez que, one time this membrane broken, the bacteria die. So this is the proper purpose of the peptides or antibiotics medicines. So it is our focus of our study. So this is for me, it's very beautiful, this bacteria, very colorful, very safe, because in the screen. And this is a scheme of how you treat my membrane. In this study, we study five kinds of the chemotypes of this membrane. So the a parte lipídica, I forgot the words. The lipidic phase, like this, is the same for all, and these different colors is different kind of the bacteria. And all this is being seen in the lab, in experimental. So this is this kind of the sugars that you put in different colors to see the different size of this. So this I will show you how we can represent this, modeling this different kind of membrane, and you can study with this. So just some numbers, how do you see the size of our membranes, and all these membranes you will simulate for at least 200 nanoseconds after you use already simulate equilibration of the rough LPS. So very stable systems, you can guarantee. This is a kind of the system setup, but I think that if someone have a question, you can make me later. So what this kind of properties you can see, this is different, the membrane thickness is espessura, eu não sei se em espanhol é alguma coisa parecida com isso, mas this thickness is the distance of these two heads of phospholipid groups. So this is essa é a menor de todas e essa é a grandona. É a maior com mais açúcar, the biggest units of sugar here. So what you can see, when more you put sugar in the surface, you change your chemotype, you have less thickness. So the membrane is making smaller, then more, ela fica mais fininha aqui. And you can see this, and distance here is this distance here. So the lipidic phase is compressed like this. Is probably because the high interaction with the sugar with the metals in the environment. So, and you have a little bit more flat membrane too. If you have a more simple membrane, you have some undulations here, and you will see this before. This explanation, how these membranes, these chemotypes of these pseudomonas works. You can see how this affect you if you contact with antibiotic modeling. So you can see too area per lipid head groups. So is how the compressed membrane you have, and how the diluída, I don't have in English for this, mais diluída você tem. So you can see the area of these head groups. Again, if you have a small area, the membranes prefer being more closer together because this interaction. And if you don't have a lot of sugar, you have more space between these heads. And also you can see the density profile is how I put the point here, and they analyze in different fatias, assim, eu esqueci a palavra. Enfim, como se eu conseguisse fatiar. Can I do some slices? I think it's slices of this density profile. So what you can see our model has a good agreement with experiment. Of course, in where you have lipid chains, you don't have water. So this is like a black line. If you have a black line, you can see there a lot of water there because it don't have making any sense, chemical sense, you know. But you need, when you start a new kind of molecule, you need to try this sample to see if your representation is good, because all time you do something in computational and you use a software, they will answer some number. And if you don't understand what you are doing, you always have an answer, but you don't know if this answer is good or not. Is it valid? Is it have any sense? You know? So you can see these molecules very well designed, and the phospholipids here, or the phosphorus groups, is very represented together. The Ca, calcium ions. So it is expected that the ionic bond here is very close to, so this is what made the surface more closer in the top. You can see also diffusion coefficient. This is how the ions in the surface can move, and this is important to study zeta potentials of these surfaces. So the experimentalist has this information, so you can see if our models represent well this formation. So why these two different chemotypes in specific has properties too different, and we will try to answer this. So you can see you have anionic groups here, CO, carboxylated, and phosphate group. They grab the calcium ions in the surface. Is too hard to move that. And in case the lipid, you don't have it, so this is more able to walk in the surface. You can show this is how how many ion calcium is near of your structure. You can see this if you have a lot of hydration or not, a lot of water, who makes your first layer of solvatation. You can see in this study too. This is how the number the water's molecule around the calcium ion. So of course, then you have a small bacteria, kind of bacteria in the surface. You don't have a lot of the ionic sugars there, so you have a lot of water. The ion change, bind with one group, but you don't have another group near to make a bridge. So the water circle make you around of this design. So let's see. This is stability. This is kind of start being a new part of this study, is how the electrostatic interaction of this surface. This is different kinds of molecule, and you will see how the stability is directly correlacionado com a estabilidade da molécula. So you first use this kind of potential electrostatic, the Poisson-Boltzmann, and you can see how the electrostatic potential change ao longo do eixo z-axis. So they started, our interest is how the potential works in the surface, outer surface, of course, because this is responsible to attach or not attach the systems or materials or peptides or antibiotics, and so. So, of course, the lipid IA have a little bit different potential than another ones. Here, electrostatic potential, this is only positive, because probably because the exposition of the group, the K group, and in another case you have ionic sugars in the top, so you don't have calcium ions enough to supply to neutralize the surface. So is this what make his that then so different? So yeah, and here you put the two graphs together to see what this occurs. Let me see here. Okay. So the last residue, you have low potential here, but of course, what is expected when you go out of the surface, the potential start to grow up again, né? Because you have a bulk of water, so you don't have more. So it's different electrostatic potential for different chemotypes here, and you can see there's two kinds of potential. Has this GALU is more negative than RMLC, and the scientists don't understand how or why it's so different, because the difference of the sugar groups is too small. And of the difference, the last one. And this is the experimentalist. You have collaboration in Sweden, and you can see, you don't see the difference of these two bacteria. It's very dangerous, but they are very different activities from another materials. This is my friend that started the program. They start the work with the experimental bacteria. So, and here eu tinha cabelo nessa época ainda, então tá eu aqui. So to understand this, we try to look for the potential surface. You have a little bit of difference with this approximation. This GALU has a very biggest group of the potentials, positive and negative. And you see the RMLC, they're more distributed, distribuído de forma mais homogênea aqui. E a gente estava tentando, you have understand how it's possible. So the problem of the experimentalists see is called zeta potential. So the zeta potential is what occurs here. And in this another graph is what happens here. And this is sometimes is too hard for us understand it because it's too far away of our surface, far away for atomistic look, atomistic view, let's see, because what we study is kind of here, not too far of the surface, so you can see this difference. So we try another approximation. It's a kind of non-linear. In this, have this equation. Yeah, of course, you use a periodic boundary condition because you don't make sense. It's just a piece of this bacteria is all the surface of bacteria. And in this, you can slab, the word that I find it. Then what you do, we will program a new model to this model mempot, you put in software already published is Delphi. So you can study these different slabs in our surface until you can also until far the surface of the molecule is the difference. So you can see in different way how this the electrostatic representation of all molecule and of all system, and we here we put this slab that we study. So this colorful, this white, blue, and red slice is this representation. You put in this slice, you see what card charger you have, and you make the sum of this, and you can see how the properties and how one slab compromise another one. So you have this conjunct. And além de, beyond we study a modeling of this molecular this molecular membrane, you will also implement this program, this kind of program. Let's see. See, was a cover of the computational chemistry. It was very nice work to do with them. So we try change or put some melhorar. Improve the tool that you have to study the electrostatic properties. So this we can change. You can change the ionic force near of the bacteria too. You can make some difference with the concentration and stronger ionic strength. So you can see the difference, how this behavior in different scale of this membrane after seeing. This is a kind of the RMLC chemotype. And you choose the different constants dielectric to membrane. So you have a problem, you can choose this in this new tool, you can choose the dielectric constants for the lipid phase. So maybe you can represent better or not your system. So you would have this difference. You have more, if you put, you increase your constant dielectric constant, you have a difference of the surfaces, potential electrostatic in the surface or Rosetta potential. And this is another result. So you can change it. You can use two different potential, electrostatic potential for your system, just the internal membrane that you don't have, you're just modeling in the outer membrane. So that's different behavior too. Now to finish, it's important to everybody that study a material, a hard or soft material, is what is surface. Is maybe to experimentalists is more easy to say, can you see, you can touch the surface. But depends of your molecule. If you have a kind of surface, a metallic surface or ionic surface, is very rigid and very well behaved, the surface. But you have a soft material like this. This is the part of this gray area, is like a LPS part, if it's lipidic part. But this is colorful, is a part of your membrane that made of sugars, rings of sugars. So what you expected be the surface, because don't have a defined surface. So you can choose your membrane. You can have because the water can go down in the sugar surface. So see if the water can came down in your system. This is kind of surface too. So you have a deep surface and the superficial shallow surface. In this shallow surface is just the water that is near of the principal groups, or the groups of the ionic groups is far away of your lipid groups. You can assume this is a kind of surface, or depending of your adhesion of your material, you can use this kind of surface, because if it's like my sponge, you can grab the molecules of the water inside them. So it's a kind of surface too. It depends of your question or of your model. You need to study this behavior of water in the science too. And of course, we can just to see, you can study the behavior of the water in this kind of surface. If you study, of course, I don't make any sense I study too far of my surface, of any kind of surface of water, because you have a book of water, and the water is not have a organization, of course, but you have in this deep surface, you can see some kind of organization for this kind of chemotype and molecular, and this kind of chemotype. You can see here you have more molecule organization near of the surface. In the case of the RMLC, you have organization a little bit more away of the surface. Though this is my acknowledgement, and was the guys with work with this membrane, some guys of the UFPE, the UFAO. My student was my student in the beginning of this work. Now is a doctor in France. These my friends, these my co-workers too in the US, in Minas Gerais também. So I really hope that you enjoy the presentation like me, and you understand something of my English, and that's it. I'm open for questions.
Thank you very much, Roberta. I really enjoyed your talk. Thank you very much. Now we will make some questions. Please, the first person we invite Professor Stuart Holmes from University College London. Stuart, do you have any question?
Thank you, Roberta. It's very nice talk. It's a very complicated calculation. You have many, many variables. How do you confirm that your program is correct? Do you pick some simple physical, some experimental values and then try and confirm those? Because you've got so many variables. How do you confirm your model is correct?
The first of all is you can see the properties is is from basic science. If like this, the water can be stay together with lipids kind, and another is the area from lipids in the size and thickness of your membrane. This is, you have experimentalist study to confirm that we are you are the right way.
Yeah, the right way.
Yeah, you need it, of course.
I have one other question. It looked on page 29, you have a high electrostatic energy over a small distance. Does that translate into high electric fields? Perhaps? Are there high electric fields in the system?
Let's see.
I think
This one or another?
There's one before, page 29, I think.
I can see the, let's see.
Before.
I need to change the...
Slightly earlier, yeah. Oh, must be 28. Sorry. This one, thank you. Do you have high electric fields in the material? You have an electrostatic potential that's changing very rapidly over a small distance. Does that translate to electric field?
No. This is this is because the properties of your group, because you have your ionic group. In this, let's show another one. This maybe is, you can see, maybe is easier, a little bit more easy to understand it, because here in the colorful lines, you have a ionic group. So when you don't have a charge, they have a potential because the ionic strength of your environment. So if you have a phosphorus, PO4 or COO minus, you have a down of your electrostatic field. or electrostatic potential, because it's like I was a point, and each slab of this my system, I measure the medium of all these dots. So I'm up, up, up until stay near surface. Was clear?
Yeah, that's clear. Thank you. Thank you. You've made a very complicated subject sound very, very easy to understand. So thank you for your talk today. It's very nice. Thank you.
Welcome. Maybe if you have another question or more specific question, if I can answer, I don't have in English enough to speak with you.
It's just fine. Your English is just fine.
You can write it, maybe
Thank
write
you. I'll get your email.
work
Thank
better.
you. Thank you.
Thank you very much, Stuart. Now we invite Gabriela Grat from Universidad Nacional de Córdoba. Gabriela, do you have any question?
Hello, Roberta. Your talk was very nice and very complicated system. I wonder all this coarse grain method is classical, isn't it?
Yes.
And do you have a code or how?
Yeah, it's very common. No, it's very common. It's very has a very I need a help here with my English. Muito estabilizado. Os programas já estão muito estabilizados. Well established. We have a software is available, a lot of software available, well done, established.
And which is the code?
Você lembra algum de coarse grain? Porque o Gromux faz isso. Gromax do this.
Gromax. Okay.
Gromax do this too, but you have another. So just now I don't remember, but I can send you. Huh? Martin. Martini from Uruguay.
And also with lamps, you think calculations? Lamps is also for classic stuff. For many.
Code? It's a code. So lamps works too, but I don't know if it has the coarse grain too. Yes?
Okay.
Coarse grain too. Let me ask you.
Also has it. And this works in combination with quantum methods, with quantum codes, or you obtain the potentials, or well, I wonder how this works.
No, just in here you don't use the quantum mechanics just to get some properties of one unit of my membrane, like LPS and the sugars. So if how example, I can study better how the charge of different atoms behavior this, because the Gromax and the force field Gromax don't have this specific kind of sugars. So I need to make two force fields. And after this, after I extract this information like charge and potential, I put in the force field and run just for molecular mechanics.
Great. Very, very interesting. My other question is because I don't know what is the function of water in all this system. It's something very chemical or biological. Well, I don't know why water is so important.
The water is all the system, biological system works within water. So you need to understand how the behavior, because the behavior of water in the surface of any materials is important. Because if you have a behavior of the very stabilized ions in the surface of the membrane, maybe you can change you can put a peptide here or antimicrobial here, and the drug don't have adhesion, you know, because the interaction with the ions and solvated the first layers of this water is energetically more stable than the interaction with the medicine. So you need to study how this works in the surface.
Okay, okay. I think I am starting to understand. Okay, thank you very much.
Well, thank you for your questions.
Thank you very much, Gabriela. And now we invite Professor Augusto Moreira de la Universidad Federal de Pernambuco. Augusto, do you have any question?
Yeah, a lot of questions, but just one here. I work with Roberta. It's a pleasure to see Roberta. She's in Spain, Bilbao now. Yeah,
After you go the
eating
study.
paella, and I see a potential surface that had a lot of peaks, and in the cost grain version, these peaks is there is an absence of these peaks, and the question is only the valley is important in the model, or these peaks can be have an I don't know.
Speaking in Portuguese, what you know about the I'm sorry, guys. I need to understand the question. Você quer saber o valor?
Coloca um dos primeiros, eu acho que o quarto ou quinto, esse?
Esse?
Não, o anterior.
Peraí.
Esse. The cost grained é o que você usa.
Não, esse é um modelo que pode ser usado. O que eu usei foi o atomístico.
O que você usou foi o da esquerda, então.
Isso.
Aí tem muita diferença entre os dois modelos? Os picos, eles alteram muita coisa, não?
Sim. E você pode... I will try. But after 2 weeks, you can join a coffee and talking about this more. But is because in coarse grain, you reduce the places that your system can pode alcançar, the reach.
Okay.
You know, so because when you have, for example, methyl group, that is a carbon with 3 hydrogen, you have 4 different atoms. You can choose, you have mobility. Then when you change for coarse grain, you just have you have a ball, a sphere that represents these 3 atoms. So you can clear your surface because you restringe a number of the atoms of your system. Então, você troca um CH3, que são 4 átomos, assim, tem o átomo à mão, né? Tem os 3 assim, e você troca para uma única esfera. Então, a mobilidade dela e os lugares que ela pode alcançar na potencial já vão ficar diferentes. Então, você mapeia melhor. But with this, you can use choice answers of your model. What you want with your model. What kind of answer you wanna. If you need a specific answer about the atomicity, the coarse graining can do this for you. But if you wanna see how the behavior of all system, not with the exterior, but how this modeling, how this protein can fold or not, maybe coarse graining is better for you.
Okay, thanks for the answer. I will stop here. Thanks.
Thank you, Augusto. Now we invite Arturo Martinez, del Simvestar de México. Arturo, do you have any question?
Muchas gracias por la presentación, Roberta. No, no tengo preguntas. Muchas gracias.
Thank you very much, Arturo. Roberta, I have one question. How expensive computationally are these simulations? How long does it take? Because normally you're using molecular dynamics, but you also have a lot of atoms.
But now, if you have before, when I started this, you have 2 or 4 to run. Now, with the advanced, of course, you have a 4 too, but you have the system with more GPU computers. So this GROMACS has they can distribute your GPUs to run. So you have a 4, but not the same. Maybe let me check the part of my quantas CPU você lembra? Quantas CPU a gente usava? I don't remember the specific the quantity para rodar as membranas. Maybe the number we have 2,000 CPUs, GPUs to run this kind of systems. So when works, né? To works, that when works you can take a coffee and wait running, but until the model is good, I spend to set these parameters well. I spent 2 or 3 months just trying. Was very era muito frustrante. It was the first 3 months of like a postdoctoral, so was very difficult. But after then, my model works, so it's available for everybody. So it was published then.
Okay, and if I understood well, you use a code, an available code, but you also did some algorithm by yourself. Is that true?
Yeah, this is a collaboration with Clemson University that we changed the way they calculate the electrostatic potential. So in the GROMACS, we have a regular formal to do this. Is like a boson like this. And we with this collaboration, you change the way you use another equation, another approximation to understand how the approximations, how calculate the potential. So in the GROMACS, you can just do the slab, different slabs, sum of discharge, and you have a medium. And our approximation that you put in Delphi software is a module of Delphi, now called main pot. You can use a different, you use a slab to calculate to the electrostatic, but you can use a different dialectical. So if your system, you can use a dialectical different here because they are hydrophobic, and here is hydrophilic. You can use a different dialectical to estimate it, or change your strength, ionic strength too. So it's a little bit, and this is us. See. I lost it. It's a cover of the journal. I think it was my first cover. I really like this cover. I don't know where I put this in this present. This is very beautiful.
Okay.
Is available too.
Okay. Thank you very much. Very nice pictures and very nice talk. Do you have any final words to say, to share with us?
just I'm really sorry for the broken English that I forgot that I needed speaking in all in English. I really forgot this detail. So I'm really sorry, and I'm open to answer or collaboration with you, or answer some questions or doubts that you have about this work or another works of soft materials, not or biological soft materials. I'm here. I'm open to questions or collaboration if you have. It's a different viewer. I know that very fun. When works is very fun.
Thank you very much. Every Saturday we have a talk like this, and you are invited if you want to be with us in the future. And now we ask you to stop sharing your presentation, and we ask to the panelists to put the cameras, please. And I'll just say goodbye to Roberta, and thank you very much.
Gracias, Roberta. Thank you.
Bye, guys. Thank you very much for inviting me here. For me, it was very fun.
Bye.
Bye-bye.
Also for us. Thank you. Bye.
And if you wanna go with Brazil, come with us. Come invited.
Okay.
Our campus and
Okay.
Bye-bye.
Roberta, if you leave, everything will close.
So,
Okay.
bye.
Bye-bye.